Okay, we're back. So continuing on, then we have weak bases. Weak bases are those that do not dissociate 100% in water, just like weak acids. They are weak electrolytes and weakly basic. For example, ammonia is a weak base because it cannot completely dissociate in water. It has nothing to dissociate, and so what it does, it actually rips water apart as a hydrogen ion acceptor, and that is where its basic activity comes from. So it can't possibly be that strong because there's nothing to dissociate. Now, we then get into what's called a conjugate acid-base pair. Now, a conjugate base of an acid is the substance with one less hydrogen than its parent acid. That would be the conjugate base of an acid. So the example we're going to give for this one would be HCl, which would be the acid. Its conjugate base would be what you take one hydrogen, when you take one hydrogen away from this, what's left, and it would be the Cl minus. And that would be its conjugate base. Okay, so this is the acid, because it has the H on it. When you take the one hydrogen away, that's the conjugate base. Okay, then we also have the conjugate acid of a base. So the first is the conjugate base of an acid. Now we have the conjugate acid of a base, which is the other way around. It's a substance with one more proton than its parent's base. So, for example, HCO3, yes, there's an H on front, but it's got this minus here, which means it can be a hydrogen ion acceptor. And when it accepts the ion, or actually, wait a second, I lied. This would donate the proton. And so this would be the acid. Make it smaller. This would be the acid. This would wind up being the... Okay, so this would be the acid. This over here would be its conjugate. Oh, that's ugly. This one over here would be its CB, or the conjugate base for this particular acid. We will have more practice with this later. Okay, now, if HCO3 is an acid, then its conjugate base is CO3 2-. Acid, conjugate base. If H2O is a base, because it accepts the proton, this hydrogen comes here to H2O, its conjugate acid then is going to be H3O+. Okay, and this introduces an interesting property here. Okay, and this property is called amphoterism. And an amphoteric substance is a substance that is capable of behaving as an acid or a base, depending on its conditions. So, for example, water, H2O, has both hydrogen ion and hydroxide ion. So it can behave as either an acid or a base, depending on what it's reacting with. Okay, so that brings us to measuring the strengths of acids and bases. Okay, so first, the self-ionization of water. In order for us to really measure our acids and bases, we have to realize that water itself, in its own, when it sits in its own soup, when it's just water sitting there, the water itself will dissociate to some degree. Okay? And in the water itself, the concentration of both hydroxide and hydronium are 1 × 10⁻⁷. Okay, so I want you to think about this for a minute. Water actually dissociates itself. So we're going to write the equation that works with this. Okay, this is, by the way, what makes water neutral, is that these two ions are balanced. So here's what it looks like. It needs to be a little bit bigger. Now this happens between two hydrogen molecules, or not hydrogen, two water molecules. Okay, so we have an H2O. Okay, and then we're going to have another H2O. To make. Now, when one of these hydrogens gets split up, gets ripped off of this one, it's going to leave behind an OH minus, and then the hydrogen goes to the other water molecule, making it an H3O plus. And this right here is the dissociation equation for the two water molecules. That the OH minus and the H3O plus are the outcome of one of the hydrogens leaving one water molecule and joining the other one. And we will draw this better when I get to school and I have my slates ready for you guys to show you what this looks like, because it's too difficult to draw without a pen. Okay, now the equilibrium constant for water then is the Kw, and all acid-base solutions is calculated by this. Now we would make this because water isn't involved; it's just the products, right? So we just find the how would we set it up? We would take the concentration of this times the concentration of that. So we would take the concentration of the hydronium, multiply by the concentration of the hydroxide, and what do we get? Well, if this is well, that's not entirely true. Hold on. It's products over reactions. So that should actually be a negative in there. So let's make that little negative. It's 10 to the negative 14. Okay, now water then are these two concentrations, okay, mixed together. That's what gives us our 1 times 10 to the negative 14. So, when the hydronium concentration then increases, when one of them goes up, the other one has to go down. Because if we're making more acid than the other one, okay, in order to maintain this negative 14, okay, these two are inversely proportional to each other. So in order to make one go up, the other one has to go down, because this is an equilibrium process. Again, we're just going to keep going with this one. Okay, so any solution then with a hydronium ion concentration greater than 1 times 10 to the negative 7th is acidic. So if it has more H pluses, then it's acidic. And if it has less than 1 times 10 to the negative 7th, it is basic. And this brings us to pH and pOH, which we will hit in part 4.